So please welcome Dr. Wright. I will share this, able to share screen. Okay.
All right, can you see my slides?
Yes.
Perfect. Here we go. This is a secret I learned recently, is the pointer option and the laser pointer. So much fun. So I am Jessica Wright. I'm a research geneticist at the USDA Forest Service. And I'll start for a second and just talk about what that means. I'm not change this view. I don't need to see me. I do research. I'm a research scientist. I'm promoted based on papers and grants. Unlike a professor, I don't do any teaching, and our service is very different than what professors do. So I do research, basic and applied research, and recently I've been focused on seed transfer here in California. And I've been working in this post-fire landscape. This is the campfire in Northern California. This one was pretty devastating and disastrous, and you guys probably heard about it on the news. But this was a fire that moved super fast, and it burned a lot of stuff really quickly, including several towns. We're outside of the town of Concow in the Concow Basin. That's the Concow Reservoir in the background there. And this is a landscape actually that's burned twice in the last 20 years. It burned also in 2008. And so in fact, these dead trees we're looking at here died in the previous fire and then got even more charred in the campfire. So it's a pretty obviously used to be forested, but not really forested anymore environment. And a forest manager has to make a decision about doing reforestation. Are they going to do it? Where are they going to do it? Where are the places on the landscape that are the most in need of reforestation? And what areas is it going to be most effective? And those are all really important and very interesting questions, but not the one I focus on. I focus on the question after the decision has been made to do the reforestation activity, what seeds do you plant? And can we use naturally occurring genetic variation to increase the likelihood of success of a reforestation project? So I'm looking at the question of what seeds do we plant, and not the question of where do we plant or do we plant, but after the decisions have been made to plant, what seeds do we use? What are the best seeds? And of course, the seeds go to the nursery, they become seedlings, and then they get planted out here. And in fact, I just got funding. We're going to be doing an experiment on this exact chunk of land right here, looking at different seed sources. And I'll talk more about that as we move forward. So I want to talk a little bit about trees and why these issues and questions are really so complicated. This is a picture of my grandmother. She was 99 when this picture was taken. She just turned 101, and we had dinner with her on Saturday just before Easter. And you can see she's been around a long time, and when she germinated, the climate was quite different, but she's been able to move around. She's moved all over the world. She lived in India, New York, Texas. She now lives in Palo Alto. She's been able to kind of adjust and go to climates that she has appreciated and liked over time. The redwood tree behind her germinated a lot longer ago, and it hasn't moved an inch, well, maybe a couple inches, but it's not moved from the place where it germinated. And so whatever climate has happened there, whatever's happened at that location, it's just had to put up with or die, essentially. There's no picking up and moving at this point for that tree. So as the climate change, a tree has to be able to respond to it and have the necessary genetic materials and makeup to be able to withstand the climate at that location. And so it actually turns out a lot of trees, there's a concept called adaptational lag, where trees are actually adapted to climates that are not the current climate, but the climate that happened when they germinated a long time ago. And you can kind of see that here in this graph. This is a seed zone in California, and I'll talk a little bit more about this later. It's just a place, and if we go across an elevational transect at this place, and we go from really low elevation up to really high elevation, the first thing we notice is that the temperature, it goes from, okay, so I'm back over here. So we have purple is the temperature from 1961 to 1970, green, kind of a current temperature, 2009 to 2018, and then the orange is a modeled future climate. So we kind of look at the current and maybe recent past climates. You can see as you go up in elevation, the overall mean annual temperature goes down. We go from over 16 to, over 6. So 10 degrees of difference between a 0-foot elevation and 10,000 feet elevation. And you'll also see that at each of these elevational bands, there's been warming. So a tree that started growing at, say, 5,000 feet, now this is a climate in 1961, if they germinated, at that time, and they're now experiencing this climate, and here's the climate they may experience in the future, and that tree isn't going anywhere. It's not moving anywhere. But can we think about matching those climates? So if this is a future climate, well, what if we took a tree that came from a similar climate today? So maybe go downhill 1,000 feet or 2,500 feet and find a tree that's adapted to the climate that is going to be at that location, rather than a tree that might be adapted at that same location, but to a colder climate. So my work has been focusing on selecting the source of seed in post-fire reforestation projects in California. And currently we use the California Seed Zone map. I like to use this picture because it looks very old. And it is very old. It was developed in it kind of first started getting used in 1970. And the idea is that trees are moved safely within a 500-foot elevation band within each seed zone. Now, one of the really useful things about the seed zone is it does help to determine cone collecting needs. So you can look in the freezer and say, well, how many seeds do we have for each of our seed zone and elevation bands, and how much do we need? And be able to catalog your seed collections really well. An interesting feature is there's only one map for all tree species. And so is it the same for pines or Doug fir or oaks or other species? That is, I think, a really important question. And I will point out it's a map. It is a geographic thing, and it's not really set up to deal with a changing climate. It's very static. It's not flexible for changing climates at all. So how does this map work in a changing climate? And so our goal is to develop a more informed use of the seed zone map in a changing climate to increase the productivity of reforestation projects. So I've got a team working on this project together, and we are funded by CAL FIRE, which is the California State kind of forestry department. They focus a lot on fighting fires. We've got Jessica manages the seed bank at the LA Moran Reforestation Center. That's the California State Seed Bank. And Stuart and Anthony is the director of the Reforestation Center, and Stuart is a deputy chief for reforestation. Obviously that's me there, and this is Jim Thorne from UC Davis. He is a geographer. Joe, you'll hear a lot about Joe Stewart. He's a postdoc, and you'll see a lot of his work he was doing. Ryan is a GIS specialist, and Michelle Stern works for the USGS, as well as a grad student at UC Davis, doing a lot of really interesting work on climate modeling. So our approach that I'm going to talk about today is to talk about provenance test data and results from analyses of this kind of data, and I'll define this in a couple seconds. And we're going to apply those results to the climate data and the California Seed Zone map. So provenance tests, what are they? They are tests where we collect seeds or acorns from any number of locations across a species range or an area and plant them into one or more common gardens. And they're really the gold standard for testing how trees grow in a novel climate. You take trees from all kinds of different climates, stick them into the same climate, and then you measure them for growth and performance and other traits. I'm working on a paper right now looking at the phenology of budburst in oaks collected from all across California. There are historical tests that are available, and new tests are being planted and evaluated. So just to show off some new tests, we have 2 tests I've planted recently. This is the Valley Oak Provenance Test I told you about. We've been looking at budburst and growth and all kinds of traits in those trees. And this is what I call an operational reforestation test, an operational provenance test, where we planted 12 sources of sugar pine and 12 sources of ponderosa pine into the burn scar of the King Fire, which is another big fire in California that happened several years ago. And we're going to be setting up a replicate of this, or a similar test to this, on the campfire at that picture I first showed on my first slide. So planting trees from different sources and different climates into the same environment and seeing how they do. So Joe has been gathering up a ton of provenance test data from all across the Western United States and Canada. And you can see here, I'm going to show you data today from 5 species. I think he's up to 14 at this point. Got white fir, Doug fir, ponderosa pine, lodgepole pine, and Western hemlock. Now here's the basic hypothesis, which came from a paper another postdoc I worked with, Luke Brown, did on the Valley Oaks. So our hypothesis, if we expect to see local adaptation, here on the x-axis, we have the difference in temperature of where the seeds came from and where they're growing. So if it's here on the right side, they're planted in a place that's warmer than where it came from. And it's over here, then it's planted in a place that's colder than where it came from. And here's where there's no difference of where it came from and where it was planted. Now, if there's absolute local adaptation, you're going to see the best performance when trees are transferred the least distance. But if there's an adaptational lag, like I was describing before, the trees will actually perform better if they're planted in a place that's colder than where they came from and not the temperature of where they came from. So Joe gathered up a ton of data, and that's the point of this slide, is just to show off all the data and also to walk you through the axes, because we'll see several graphs like this coming up soon. So this is that same transfer distance. So this is zero change in temperature. I think he was using Tmax on these analyses, the maximum temperature on these analyses. So these are planted in a warmer place. These are planted in a colder place. And I think one of the really great things that Joe put together was the relative volume per hectare. And so that was looking at both growth and survival and how much tree volume there was on each hectare that was planted in these provenance tests. So this is the data we have, and here are the results. We see evidence for adaptational lag in all 5 of these conifer species. So again, you have the 0 line where there's local adaptation, and you'll see all of these curves are shifted more or less to the left. They all perform best when they're a slightly colder, planted in a slightly colder place. And that's shown over here with confidence intervals, which lets me go on a small digression about the importance of having really good data. And basically these tests here that have the smallest confidence intervals are the ones that have the most trees that are planted. And these ones with larger confidence intervals are smaller tests that have fewer trees. And so with better data, you get more data, you get smaller confidence intervals. So I think this is really important to consider in seed transfer, because seeds are already not adapted to the climates where they're being collected, but in fact, they're adapted to a slightly colder climate. So how much of loss of tree volume can we expect if we don't actually move seeds? So you'll see here, this is kind of flipping that graph around. This 0 now is not 0 transfer, but this is 0. This is the height, the volume we'd expect at the optimal temperature for these trees. And if we miss that optimal temperature by 2 degrees Celsius, then we expect to see a 12% decline in volume. And over here, if you miss it by 3 degrees, we're looking at over 25%. And this is true in lodgepole pine as well as ponderosa pine. Again, fewer tests in ponderosa pine, so these confidence intervals are much wider. So how do we use these results? Let's apply these expected reductions in productivity to the climate models across the California seed zones and model current and future climates in each zone. So what does this look like? So Joe put together this tool, and I think the website will be coming up for it. So this is the blue area is indicating the planting site where you want to plant trees. And hey, here's that seed zone 526 again, which we were looking at earlier in the talk, from 4,000 to 4,500 feet. And the tool selects excellent matches, good matches, and passable matches across all of California. It's bounded, I think you can select how many degrees of latitude you want to bound it, or sorry, longitude you want to bound it with. So it's using the climate for the seed sources from 1940 to 1969. And those are not going to change because those seed sources, the trees are there, the seeds are collected, but that it doesn't really matter that those places are getting warmer. That's what the seeds, where the seeds are. Now the future climates for the planting sites, we use the means of 10 loca GCMs, the centroid of a 19-year period. And here is the website for the tool if you want to look it up yourself. So the tool generates a report, and it shows you what the best matches are across California, and it gives you the expected decline in productivity for each of these matches. So for this seed zone 526, now these two seed zones here, actually 120 is down here and then 352 is this one right here. And there's actually a lot of genetic data that suggests that Sierra and Coast Range populations are very different. So I would actually argue that we should not consider those, but in fact go to the nearest Sierra source, which is 525, a seed zone north, and downhill quite a bit, 2,000 to 2,500 feet. And remember, this decline in productivity is coming from this same curve. It's all using the lodgepole pine data. except for now it's working in a 4-dimensional space. There are 4 different climate variables that are used. So this is just mean annual temperature. There are now 4 more variables that are in there that allow for this 4-dimensional space in climate space to be determined. Now, what does this look like? So here's for our seed zone 525 at 2,500 seed, the planting location. This is not going to change because, or sorry, the seed sources are not going to change because they're the older, they're using the seed, the climate data for when the seeds were collected or when the trees were not first germinating, but earlier in the tree's life. Now the planting location, that's going to change as we look over time. So this is 2040, and this is considered a pretty good match. So here are 4 climate variables: mean annual temperature, mean annual precipitation, temperature differential, and mean cold month temperature. Now, if we zoom forward now to 2060, you'll see that our seed sources now are not quite as good of a match. This has gone down to the light green category, a passable match. And you'll see now they're not quite as lined up. And if we go down one more, now we're at 2080 in the modeled climate for 2080. And now the seed source and the temperature at this from where the planting location is and where the seed source came from is quite different as things continue to warm up. I think it's one of the important questions we're grappling with is what is the right age to look at for what time in the future to project to try and match the climate to. Do you do it when a tree, so if you're going to plant it now, this tree is 60 years old, when it's starting to produce cones and being productive, or do you use an earlier time in the tree's lifestyle? And that's a question we're really working on right now. So if we go down here, hang on. So now, what does that decline in productivity look like? So remember, 2040, we had a 1.8% decline in productivity. I'm going to walk through this graph because in the next slide you can't read anything. Probability density is this thing. So most of this is comparing across the seed zones. The seed zone's a large geographic area, and comparing the climate at each location or a set of locations within each seed zone for where the seeds came from and where they're being planted, and then calculating this decline in productivity. And this is the probability density across that seed zone. And this is so this is the density. So the higher this is, the more there are. And then this is the decline in productivity, 0, none here at 0, 15%, quite a bit. So just remember that's what the axis is. And you can see here in 2040, this is that we have the 1.8%. In 2060, it's 3.8. And in 2080, it's 9.37. So you see how that decline in productivity as the temperature continues to warm over time is going to be is going to get more and more, and definitely a question of what is the right time to line trees up to. So I just want to show one more match, which was to go just downhill and say, let's go down. So we want to plant at 4,000 feet. Let's go down 1,000 feet. And here we get a pretty good match. It's 2.5% overall on average if we could just go downhill. But I think what's cool about this tool is it shows that while that's a very simple way to do it, that in fact, a better way is to go to a slightly different seed zone. Here's what that going just straight downhill looks like in 2040. And you'll see it's an okay, you lose 2% of your productivity. And you can see there's a pretty good alignment of the different climate variables, but certainly not as good as the best match that we found. So my take-home message is the California Seed Zone map has been used since the 1970s as a guide for seed transfer in reforestation projects. We've only had one map for all species, and there's really no way in that map to account for a changing climate. And working with CAL FIRE and the Forest Service and UC Davis and the US Geological Survey, we're exploring how seed transfer using the map could be impacted by a changing climate. We're trying to expand what data is available for deciding where to get seed sources using, for example, the Provenance Test data I talked about today. And these results will help to inform seed transfer and the use of the seed bank, both at CAL FIRE and the US Forest Service seed banks. And that is my talk. Thank you so much. And I will stop sharing.
You start video, share screen. Oh, where's my PowerPoint? Here it is. Okay, and then can you hear me?
Yeah, we can hear you, Lynda.
Oh, thank goodness. Slideshow. I have my tech guy right here. Woohoo. Okay, how's that look?
Looks good.
Okay, good. All right. Wow, I'm really
really glad that Jessica talked about the tree seed zone issue, because now she won't think it's simpler, but compared to the Willamette Valley Prairies ecosystem, it is simple to at least do the modeling. So I kind of wanted to just look at sort of what's our reality in the restoration of Willamette Valley Prairie and what really makes practical sense. And I'm going to give you a little bit of past history and sort of got to look at the past to see the future, I guess. So just some background. This is a slide I've used in a bazillion talks by now. But so what is the Willamette Valley ecoregion? We're talking about prairie prior to 1850 was pretty much the entire Willamette Valley. And you can see that all the, does this pointer show? Yeah. Does it show to them? Even though it doesn't show to me. Sorry, I'm new at this. So open prairie is all the lighter peach areas here. The darker peach is savanna. So that had oaks and ponderosa pine, valley pine. And it's really a small ecoregion, really small. It's 40 miles or 250 miles long and 40 to 70 miles wide. You know, we're not talking about the Great Basin. We're not talking about the Midwestern ecoregions. The Willamette Valley is really teeny tiny. In fact, I've talked to people in the Midwest and Canada who go, prairie, Oregon? So it's not well known. So where we are today is, of course, less than 1% of prairie left in the Willamette Valley, and most of that is actually very highly degraded. Many of us have probably seen that. So, we have a long road to go to restore this habitat to any kind of functionality. So what I thought was really interesting to look for this talk, because I sort of know it intuitively, but I decided to sort of look up where a lot of the species we have grow. And some species are very, very large ranges. So this is Colomia grandiflora. That's it. There's no varieties, no anything like that. So we're talking most Western states has Colomia grandiflora. Some Willamette Valley prairie species are strictly endemic to Oregon and the Willamette Valley. This is Sidalcia campestris, tall checker mallow, and it's in Multnomah to Lane County, and that's it. They've even tried introducing it just into gardens because it's a wonderful garden plant up in Washington State, and they don't even persist there. So I thought that was kind of telling if we're starting to move things around or think about it. Then you have species, Eriophilum linatum, Oregon sunshine, it grows everywhere. Well, yeah, but it's different varieties and different subspecies. And so then if you look at just the one that we have here in the Willamette Valley, it's subspecies, it's a variety, I can't see under here, a variety of lanceolatum, yes. And it's just in Oregon and in California. So that further if you start moving things around, say from Idaho, well, it's probably not even the right variety that we have growing here. So there could be genetic consequences of that. There are some species like Lomatium matriculatum, spring gold, love this plant. It goes all the way from Canada and Western Canada through the prairies of the San Juan Islands, down through the Miami Mounds and near Olympia, down into the Willamette Valley, and it's even in Northern California. So again, is it prudent if we're wondering about broadening the genetics to try to combat what we don't even know about climate change yet? Do we move them even farther afield because we just don't have answers yet? We don't know. So a little bit of background on seed movement, those seed transfer zones that Jessica was talking about. So in the early 2000s, we had a very, very narrow, most people thought that 20 miles was it, that we should, keep things as close to the remnant populations as possible. So that didn't kind of pass muster with a lot of people, but we went ahead and they put a big meeting out there among all the geneticists and restoration biologists and growers in the valley. It was led by the Institute for Applied Ecology. If you guys are not familiar with this, which I think most of you are, they have just led the charge in so much of the work done in the Willamette Valley as far as rare plant introduction and studies of our prairie plants and a lot of the Oregon species. There's a really good, if anybody wants a copy of this talk, by the way, I can save it as a PDF and email it to you. Really good information on the SOMS debate, which I'll explain in a second. So SOMS is a acronym for single or multiple sources of a species at a given restoration site. So that was the crux. Do we just use a really narrow accession, or do we use multiple accessions? And there was not agreement among people. So again, 20 miles, 40 miles, a whole ecoregion. Should you just use the species native range like Colomia grandiflora from Idaho or Montana, bring it to the valley? I mean, you can. But of course, the questions are surrounding about inbreeding depression, which I think most people were mostly concerned about was, yeah, but these are tiny little isolated pockets of prairie left. And isn't that a greater concern where that inbreeding depression could cause that reduced vigor and fitness? But then the other camp was this thing that's not very well known. It's called outbreeding depression. And people were very concerned about this because we just don't know. If you bring seed from Idaho to the Willamette Valley, that's a very genetically distant parentage. And there's some evidence that shows that there's less fitness in the progeny produced. And some show some hybrid vigor, but still the later generations do poorly. So that was the big question. So then in 2006, they decided to get everybody together and really, really hash this thing out. And lots of geneticists on the panel from all over Western states, actually, a lot of Valley people. And the conclusion of this meeting, or the results, was first they were going to tiptoe. We're going to take baby steps. So this is only 2006, mind you. This isn't that long ago. So we did a common garden study of 5 matrix prairie species. They did 4 perennials and 1 annual. And they wanted to have, this information was to inform the seed transfer zone recommendations for just those 5 species. 3 were recommended valley-wide, but 2 they actually decided there was enough morphological and phenological differences that that were probably related to microhabitats. So they didn't recommend those be for a valley-wide collection. Then they contracted with growers, mostly us at Heritage, for a couple of years to do small seed increase fields of 21 more common species, and then to just kind of see how they did in a seed production. They wanted to make sure, since we really didn't know about the differences, mostly from a seed collection standpoint, we kept the accessions separate but next to each other. So you would have a North Valley, Mid Valley, South Valley, early and late blooming accessions, upland versus wetland. And in big leaf lupin, if any of you are familiar, it has every color of the rainbow out there. So they kept the deeper blue ones separate from the whiter ones. And it was a learning moment. I was just starting in the baby stages of seed production. So I didn't do very well with these, but we learned a lot. And mostly I sort of got my comeuppance because I'm a lumper, not a splitter. So, it's all one big happy prairie species. And this picture here is of Oregon sunshine. And I hope you can see the color differences on the left here. This was a Mid and South Valley, which is a paler yellow color. And this on the right side was the North Valley accession, which was much deeper yellow. And my boss actually pointed this out. I was completely colorblind. And then there's also differences noticed between Eugene populations, which I have growing for the West Eugene wetlands, and they're almost 2 weeks earlier than the North Valley ones. So, and does that matter if we're mixing them in the Willamette Valley? Other differences, this was absolutely stunning. We had a taller North Valley. This is North Valley Aster Hallei, house aster, and this is South Valley, much shorter and squatter. It's growing on ground cloth, that's down here, so it didn't really hurt from a seed collecting standpoint. But we're now mixing them in the Willamette Valley. Is that going to matter? Because I'm growing the seed of everything. And is it going to matter in the long term? We don't know. We just don't know. Other differences have been just fascinating. This is a great paper, by the way. It's a PowerPoint, it's not a paper. But if anybody's interested in this topic, Ed Alverson wrote a very good summary of some of the differences. A lot of them is polymorphism. So it's a genetic based and morphologically based topics about our Willamette Valley prairie species and that whole, ploidy levels. Is it okay to mix them? So here is a tall checker bloom here on the right side. If you can see, notice it's in full bloom. The one on the left hasn't even begun to start blooming. It's just starting. So there's two different forms in the Willamette Valley, and I've actually seen them side by side growing in the wild together. There's a very strange looking rose checker mallow here on the right side. There's maybe a hybrid. I think it's a hybrid that's being collected out there as Malviflora. Sidalcia malviflora. Is it the same thing? It doesn't look the same. It really looks like a total cross between Campestris and the malviflora, which is this nice little decumbent plant that's a very good garden plant, by the way. Again, does that matter? That's what we're mixing those right now. So then the next step was to form a seed cooperative. And again, try to get everybody on the same page to decide for the most common species of valley-wide seed transfer zone acceptable. And for it was a big, it's going on right now. It's called the Willamette Valley Native Plant Partnership. It was begun in 2012. They pretty much just looked at what were the restoration needs and of seed that was lacking on the commercial market and in large enough quantities, because people wanted to restore it, and there's only a few growers, we're one of them. There just wasn't enough seed of enough of those species. They did set the limits to the Willamette Valley up to 800 feet. So we decided that would be prudent because higher elevation populations, there's been some reciprocal transplanting studies of Elamus glaucus, blue wild rye, some of the grasses, and they have found the higher elevation ones don't, or let's try to say the low elevation ones don't do well at the higher elevations. So this partnership, the members are providing the financial backing for the program to collect the seed and to put that seed into production with growers. And the growers are actually contracted to grow, which helps defray the upfront costs, which is a lot to start the seed fields, and then reduces the uncertainty of open market sales for growers. So contracting is really helping this program push to actually have a nice volume of seed. And then it's available to all the partner members. So, and this is kind of my summary here. So these are the points I think to consider if you're saying, well, is the Willamette Valley adequate in the fact of climate change? Because that's sort of the topic here. So some points to consider. First of all, although it sounds from Jessica's, we know it's going to be, especially in California, hotter and drier. It already is. But in the Willamette Valley, is it going to be wetter, warmer, drier, or all of them rolled into the one? We don't know. Yes, there's models out there, but we really still don't know. We just got people to say Willamette Valley is okay as a seed transfer zone. I mean, that was a big, big step, and the restoration community feels good with it, comfortable with it. Growers are doing it. There's a market for the seed. It's not sitting on shelves like it used to. So I think we've had a big step forward. So if we decide to go farther afield, to broaden the accession, or, is that going to be acceptable to the restoration community? will there be enough buyers of that? Is it practical for isolation distances? So let's say they're growing an Idaho accession or a Washington State accession, but they can't sell that to everybody, so they'll have to isolate it from a Willamette Valley accession. It's just not practical. And again, we don't know the genetic consequences of outbreeding depression that could imperil our long-term efforts in the valley. Many of our prairie species actually are able to withstand both wet and dry conditions. There's a lot of crossover species, so that will help, I think, in the resiliency, maybe not in 100 years. There's also a huge concern right now about pollinators and really focusing on, trying to get, the bloom cycles are already starting to get messed up. There's lots of research going on in the southeast states because of the shift in climate there. The bumblebees are not, it's just too hot for them to move and to follow where the plants are blooming first. So some more points to consider. It's just complicated. So like we just talked about, there's lots of good testing going on for seed transfer zones for forest species. And that's really awesome, because that's really important for financially as well as just habitat wise. So there's lots of climate modeling projects. Obviously, we just saw there's another one up at the University of Washington going on right now. But the Willamette Valley has a lot of species. And they are doing some modeling at University of Oregon, and I know at OSU on prairie species, doing modeling and actually doing outplanting studies to see how resilient our species are. But there's 600 prairie species. So obviously doing reciprocal transplanting for local adaptation or common garden studies, which look at genetic-based traits, it's just not going to be practical. And I'm just getting on my soapbox because, this is one of the most imperiled ecosystems in the world, actually. And so I feel our efforts at this point just really need to be focused on conserving the sites we have, building a more cohesive network of prairie habitats, using a broad ecoregion collection at this point, and just collect. We're losing our remnant populations every single day. I cannot tell you how many populations we've already lost, of ones that I even know about. So here's just my conclusion here. This is again my soapbox. This is the genetics we're losing right now. This was a beautiful hedgerow with a rare species of concern on it and lots of different prairie endemics, and the landowner decided to farm to the edge of the road. So those genetics are gone, period, just lost. This was a newly discovered site of Lathyrus holochloris, but it's the whim of the landowners, the whim of ODOT. Here we go. Here's an example I see every single summer. This is tall checker bloom. Okay, nice little population, and the farmer on this side is nuking his grass seed field. He's got every right to do that. He doesn't want to contaminate it. And then the road comes in here, and then they spray the edge of the road. Those are what we need to be collecting. Those are that's our genetic source right now we need to focus on. So I'm done with my soapbox. And this is a restored native prairie on one of our farms. And I'm happy to have addressed this, and it got me really thinking where at least I want to put my focus, and I think what's real that we can do. So thank you.
Thank you so much, Lynda. And yeah, everyone join me in thanking both Jessica and Lynda for their talks today. That was awesome. At this time, we're open to questions. Feel free to type anything in the chat, and then we'll try to do our best to get to every question.
I have a question for Lynda. Sorry, my hands are full for chat style. First of all, thank you both for some really excellent talks. And I was wondering, you know, it seems like dealing with climate adaptation is one concern, but there's also, oh no, oh, this is a fail. One sec. But there's also concern about dealing with, you know, non-native competitors. And so there's been work, especially by like Beth Ledger in the Great Basin, suggesting that you can have native species that are becoming increasingly adapted to like competing with non-native species. And so wondering how that plays out with your view of provenance, where if you're thinking about climate as a factor to consider, but are you also thinking about potential local adaptation for dealing with competitors? Like, you know, there's a risk of going for a lot of diversity, then diluting the gene pool for selection for dealing with competition. So I was just wondering, given that there's so many invaders in the Willamette Valley, is that part of the discussion at all?
That's interesting. There really, I mean, oddly enough, I have a tough and tenacious seed mix because there are species that seem to be the restoration of winners that we see just persisting on our sites. It's either, and I don't know if it's an adaptation thing or if it's just, for example, the checker mallows. There are things that you just find with bent grass or with tall oak grass, you know, and it could be more of a, you know, the roots are bigger, they don't go dormant in the winter. But I think, again, trying to look at local adaptation, you're talking, again, more genetic studies. And I think that gets so complicated when you're looking at the plant palette that we have. I think it's just more practical information that we're getting out of the restorations because we've been doing it for about 20 years. It's like who's winning and in what situations.
So species level. Okay. Well, thank you.
I'll add in a tiny bit with the provenance tests in the different pine species that Joe looked at. And I can tell you that the F value for that analysis I showed was 0.42. So just using the climate variables, we explain 42% of the variation. There's definitely a ton of things we are not capturing in that analysis. We're not capturing soil, slope, aspect, competitors, mycorrhizae, all kinds of things that are there. But we do explain 42% of the variation. So it's not everything, but I think it is a significant percentage of it. So that's why I'm fairly confident in these analyses. And yeah, it's something that comes up a lot, that yes, we're ignoring a lot of stuff, but it's kind of, you know, we can't, there's no way to actually capture all that variation. And in particular, the way the Forest Service and CAL FIRE uses those seed zones and elevation bands, everything gets bulked up. Historically it did, it's not so much anymore, but historically everything be bulked. So sitting in the freezer is a bag of seeds that says 526, you know, it's ponderosa pine from 526, 5,000 feet elevation. And where it came from within that seed zone, who knows? And so we can't, you know, you can't actually, there's no hope to actually match it given the seed that you have and the way it's being stored. I'm hoping that our work is they're starting to move towards using, you know, getting some GPS data. I think CAL FIRE is actually working on a phone app so the seed collectors can take a, you know, drop a pin on a map using their smartphones as they're in the field and get some more specific position data that way. But it's kind of changing systems that have been around for a long time. Like the Forest Service forms ask for a township range section, but they don't actually ask for Latin long. And a township range section is a mile square area. So a lot of those really fine scale things can't really be matched up in a Forest Service or CAL FIRE, or, you know, an operational forestry seed bank. Native plants, there's definitely a lot of site prep that comes in, and there probably is some competition with invasive plants. But with that site prep, there's kind of, they try and give the seedlings as good a head start as possible to make it. So, but again, there are definitely things that are not being captured in our analysis, but we are capturing a lot by just looking at climate.
Thanks. Yeah, that was super cool.
Do we have any other questions?
Yeah, we have one from Alejandro. It's for Jessica. Alejandro's curious to hear more about your current research on matching appropriate seed origin by climate for long-lived species when the climate is changing on the same timescale as their lifespan.
Yeah, it's a huge question because we can model climate out into the future. No, it's not perfect. We don't know exactly what's going to happen, but we can model and see how things are expected to change. And yeah, they continue to change through the lifespan of the plant. The thing is, you could, let's say we know exactly what the climate's going to be in 100 years, and we could match the seed to that exact perfect climate. The problem is that seedling still has to get through next winter. And next winter is the climate we have right now. And that might be a little too cold for this guy. So we have to kind of balance, how far out into the future you go, risking how unhappy that seedling is going to be when it starts to grow in its infancy, and thinking about, with trees in particular, that selection that happens in those early years is pretty intense. So that's one of the cool things with our operational provenance tests we're doing now. We're really testing that in a real world post-fire operational reforestation environment. I got my seedlings from the nursery. They got planted by the same contract tree planters as all the other trees on the forest got planted with. So it really is testing how they do in that early environment. And we got seeds from as wide a range of climates as we could manage across different climate zones. So we were really testing, like, if we go too far, does that make the seedlings unhappy? So I'm hopeful to see in like the first 4 or 5 years of their life cycles, to see what that survival differences are if we overshot for some of these things we took from really warm climates, and if they really didn't like being cold. So we're definitely looking at it through these operational tests. And the same thing on the campfire, we selected seedlings from local climates, but then we got pretty far afield, as far as fields we could go. We didn't go too crazy, like we didn't go down to the transverse range, and we tried to stay just in the Sierras and not go across from the coast range to the Sierras as much as we could. So we kind of tried to keep it fairly sort of reasonable, but then trying to sample as much climate variation as we could. So we're definitely testing it out. In British Columbia, they use a quarter rotation as the climate that they match to. So if you're planting timberlands, a rotation is how long you think the tree is going to need to grow before it's harvestable for timber. And so a quarter of that time is what they match it to. And then I don't like to say numbers here because then I will get them wrong because I'm, giving a talk. So I just say it's a quarter rotation. And it's about, if you have an 80-year-old tree, then that's like 20 years, is that right? So so they don't actually project that far into the future of the tree's life cycle to match that climate too.
Cool. Do we have any other questions? We got 9 minutes. Go ahead, Jeff.
Great. Thank you both for those great talks. That was really interesting. Thank you guys who organized this. This is really awesome. I have questions for both of you, I guess, but so where to begin? But maybe Jessica, just on that sort of related topic, I guess I was curious about the microclimate, how that plays into this, because it seemed like you're planting these into open areas, right, where the microclimate is going to be quite different than the under canopy areas. And so it seems like it would bias that toward preferring species, seed sources that are from warmer areas just because of that. But it seems like another challenge is integrating the sort of growth rates and fitness over the course of the whole tree lifespan, in which microclimate itself is changing too.
That is very true. One of the things we did was take GPS readings for each and every tree that got planted. And so we know where they are on the landscape. We know who their neighbors are. And we're going to be including that spatial data into our analyses. So if there are, wetter patches or drier patches on our field planting site, we should be able to account for that using that GPS data and essentially tracking, because they weren't planted in a perfect, in a Provenance test. I don't know if you can tell in the oaks, but there are these lovely grids we plant. And so the trees are all nicely in row, and it makes it so easy to measure. But on these operational tests, we didn't put out a grid. They're just kind of planted as the planters would have planted them, evenly spaced, but not gridded at all. So the planters are trained to find what are considered to be nicer planting areas, sort of next to logs or rocks that give a little bit of shelter. Because actually it's about being too hot when you're out in the open sun. The field site, the Kingfire planting site, actually gets really warm. It's at 5,000 feet, but gosh, in that full sun, it's a very tiring day working out there. It gets very, very hot. So there's definitely, it's a pretty warm environment. I think in the winter, there's also no protection from the cold in the winter, but it definitely is a pretty warm spot. So they do try and find microsites to plant into that are a little bit protected for the seedlings. But yeah, and it's definitely a concern and definitely something that's going to be changing. I think the best, again, we have the GPS data showing where each tree is planted and who its neighbors are. So we should be able to put that spatial autocorrelation into the analysis as we go forward.
Can I ask my quick question for Lynda too? Or, hey, Lynda. I thought that was amazing data you shared from the difference in phenotypes of the different seed sources. Particularly struck, I wonder if you could repeat what species that was. You had such a strong difference in phenology from.
Was that the tall checker bloom that had the early and the late blooming forms?
Like 2 weeks apart or something?
Yeah, well, actually, no, both the Oregon Sunshine, the Areophilum linatum, like the Eugene accession I grow blooms at full 2 weeks. It blooms forever, but it starts blooming a good 2 weeks before. The checker mallow is so odd, and there is ploidy issues with this. Now, whether they're connected to the blooming time, nobody knows. That's a study that hasn't been done, but it happened because my first initial collection and the Institute for Applied Ecology just collected checker mallow out in the valley, tall checker bloom, right? Then we put them in production, and all of a sudden you go and you're like, oh my goodness, there's no optimal time to collect seed because the early blooming form is done and the later blooming form is just beginning to go. And it's not just blooming, it's stature. They're humongous. These later blooming accessions are humongous. So they're actually different in stature. And so finally, I learned to do separate collections, and now I have them in separate fields. So that certainly helps. But again, they grow together in the same restoration area, in the same wild area. So they're natural, I don't know what you call them, phenological forms. Yeah, and it's just odd.
I guess my more general question that I was leading toward was whether just anecdotally even you've noticed certain types of species, certain functional groups or annuals or perennials or other groupings that have more or less sort of regional variability or more or less local adaptation. I don't know if you've done enough of this.
No, I don't think they've been, again, that was the initial studies by the Institute for Applied Ecology. They didn't accept, it was spiked primrose that was growing on really rocky sites in Marion County at Sublimity Prairie and another prairie nearby. They felt the data suggested they were so different, and they attributed it to the habitat, whether that was true, because in the Common Garden study, they still kept those differences and they attributed it to the different types of habitat they live in. So and again, there's 600 species. So yeah, there's going to be a lot of that out there. But what is it attributed to? I gave the most stark ones that I've seen.
Thank you.
And I think we have one more question, again from Alejandra. This is for Lynda. Are there enough populations of available species for restoration growing at different elevations that we could potentially use to similar types of seed selection for the future without moving outside of the valley?
Well, there are, good question. There are really nice prairie remnants above 800 feet. They're in the Coast Range mostly, and they have the exact same prairie species as the valley floor. I would advocate for maybe collecting some of those. But again, I've seen phenological differences. Oregon sunshine from high elevations blooms much earlier. It's also a shorter stature plant. So again, who you pick and choose and how do you know who to go? But I think it would help. Plus those genetics are not being captured. And that just breaks my heart that they're not, somebody is not, I am, but other people are not collecting from the Coast Range prairies.
Yeah, I guess that's also kind of the opposite direction that we typically think of, looking for warmer areas to move into cooler areas going forwards, right?
Right, so that would be, again, do we go to the Roseburg area to do Lomatia matriculatum? Okay, it's just the rogue, well, it's just one ecosystem, it's one eco, what am I trying to think? Ecoregion down. So there, and again, lots of crossover species. So if we were thinking kind of along the climate model of Jessica's, the work with the trees is, yes, warmer, move them up. But again, then you have to be careful if there's varieties or, that would probably be my next recommendation, would say to try to get some stuff from the Rogue Valley up into the Willamette Valley, with the assumption that it's more adapted to a warmer, drier climate.
Thank you.
And then one last question, and this is for both Jessica and Lynda. How do we reconcile the tension between moving species outside the local area to match the climate versus inbreeding and outbreeding depression?
Go ahead, Jessica.
I will go first. Yeah, I guess I didn't emphasize this very well in my talk, that when I'm thinking about this, I'm usually thinking about this question within the established species range. So not necessarily actually moving species outside of their local ranges, but staying within kind of where species are expected to be found, but looking at the variation within a species. And so, yeah, in trees, there's not too much concern about inbreeding depression. There's really a lot of variation. And in fact, there's not all that much concern about outbreeding depression. We did actually do for our tool a literature search, and we're about to actually upload this new feature that looking at different studies of genetic variation across the common timber species, to look at which are the ones that are getting planted the most, to look at studies that have shown where their genetic boundaries, and to let people know, hey, that climate might match, but you're crossing a genetic boundary. These are two different genetic groups that you're moving across, and maybe you don't want to do that. And that's where, if there's going to be outbreaking depression, we might expect it there. So we're actually going to be adding that little module into our tool, and not telling people, oh, you can't do this, but a little flag, hey, by the way, this is what's going on here. So we are hoping we're going to be including that genetic data from the literature into our tool. So we'll be hoping to make sure that it's there and people are aware of it. But yeah, it's interesting. There's kind of, I don't like using the word assisted migration because it has so many definitions and everybody uses it their own way. I definitely think about it in three ways. One, where you're moving species way outside of their native range. I think you guys should think about some Joshua trees up in Oregon. I think it'd be great. That would be totally out. I actually have 2 plants growing in my backyard. I bought the seeds at the national park, and they love Davis. It's great. Anyway, so we've been doing that kind of seed transfer way outside of species range. Maybe you're just going to nudge the species range a little bit. So just move it into a slightly cooler place, going to the edge of where you might expect to find the species and nudging it a bit, or staying within the established species range and just looking at variation within the species and moving that within species variation around. So I think in trees, we're definitely trying to include that outbreeding depression. I don't know that inbreeding depression is a huge concern because they're such big populations and they are wind pollinated generally, that inbreeding depression is definitely not a concern.
Yeah, sort of like what I alluded to at the beginning. I think our main concern, because prairie species here in Willamette Valley are just the opposite of the tree species. They're just populations are just postage stamps. And so I think inbreeding depression could be possibly possibly one factor. But as we said, that maybe moving from a little bit farther south up to the north would at least give you a little bit more resiliency, but again, staying within the species range. But some of the ranges of these species are quite large. So, you know, how far afield do you move them? I think Jessica's right, just nudging it a little bit, maybe, and bringing in something more from the south. And the assumption that that's going to be better adapted 80 years from now, you know, again, they can withstand, I mean, again, these are prairie species, so they're adapted pretty much to hot, dry summers. So yeah, that helps.
Well, thank you again for the wonderful discussion, and thank you for everyone who came out to listen. If there's any other questions you have, please send it our way. We'll make sure that we connect everyone. And please join us again for part 2 of the speaker series on Wednesday, May 5th, same time, same place, and we'll be listening from Dr. Sally Adkin and Dr. Tom Kay. So thank you so much.
Thank you, everybody.
Thank you, Lynda and Jessica.